Hi, so this is an introduction to Neo4j, which is a graph database, which is a completely different type of database than a relational database management system, such as the ones that we've been working on throughout this course. Typically, relational database management systems have been the traditional type of database going all the way back to the 60s and 70s. And now we're seeing graph databases because they're much more useful for being able to quickly get at data that has relationships and nodes rather than between table and table. So we're going to discuss some of the basic concepts in graph theory, and this will provide useful context for understanding what a graph database is, and we're going to use Neo4j, which is just one flavor of a graph database. First of all, what is a graph? Well, a graph is a collection of objects, each of which has a set of binary links with the other objects. Graphs are a useful way to model data for the purposes of mathematical analysis, and they have been around for quite a long time. The first use of graphs was by Leonard Euler in 1735. He used graph theory to prove that the famous 7 bridges of Königsberg problem had no solution. So if you're curious, we can talk about the 7 bridges problem and Euler's proof, but this is all deep background for the main topics of interest. So what is 7 bridges problem? Königsberg, Prussia, which is now in Russia, is a city spanning the Pregel River. It includes 2 large islands, which are connected to one another, and the riverbanks by 7 bridges. A map of this arrangement is pictured on the left on this slide. The 7 bridges problem is this. Is there any possible route through the city that crosses every bridge exactly once? Some pen and paper experimentation will quickly suggest that there is no such route. However, proving that there is no solution is much more difficult. Euler invented graph theory as a tool to aid this proof. The graph representation of the problem is on the right. 4 landmasses, each represented by a node, and 7 bridges, each represented by a relationship. So what was his proof? Well, he observed the following. The route taken within each landmass is irrelevant. Only the sequence of bridges crossed matters. Whenever you enter a landmass via a bridge, you must leave it by a different bridge, except at the start, where you leave but you do not enter, and at the end, where you enter but you do not leave. For the problem to be solvable, every landmass, except for the start and end, must be touched by an even number of bridges. Based on the above observations, the problem has no solution because all 4 of the landmasses are touched by an odd number of bridges. But if graphs are an abstract mathematical tool, why do we even care about them? We care because any data set can be represented as a graph. Any structure or any concept, no matter how simple or complex, can be broken down into a set of constituent parts that have some relationship to one another. For example, the internet can be modeled as a network of computers. At the other extreme of complexity, a single molecule can be represented as a graph of its constituent atoms, or an atom represented as a graph of subatomic particles. A water molecule or any molecules is definitely not part of my skill set, but I will tell you that graph databases can be very useful for looking at patterns and relationships, both in epidemiology as well as looking at Twitter data, looking to see who is responding to who, and who has relationships to other people. And as Euler showed, there are some clear benefits to representing data in this way. So we'll discuss many of these as we move forward, but mainly graphs are uniquely useful when answering a question that involves following a path along a chain of related items. You will frequently hear Neo4j people refer to such questions as graph problems, and they are surprisingly common in the real world. If you go out to the Neo4j gallery, you're going to see a lot of interesting use cases for a graph database. So let's talk about some of the core concepts of graph theory. Let's define the components that make up a graph. There are two of them, nodes and relationships. This is what you really need to remember. If there is basically one thing you're going to remember about what a graph database is and how it's different from a relational database management system, is that it contains nodes and relationships. Now, the original mathematical terms are vertex and edge, and in some graph tools, you will see the terms vertex and edge. I've used other tools, and node and relationship seems to be pretty common. Using these terms more intuitively describes what we are trying to represent. So let's define a node. Nodes are the main objects of a graph. We say this not because nodes contain more data than relationships, although that usually happens, but because it is perfectly acceptable to have nodes without any relationships. If you look at the opposite, it is not possible to have a relationship without any nodes. Mathematically, a node is defined as a point where two or more edges or relationships meet. This is not at all intuitive. However, it provides important insight into how graphs are used. Since the entire point of modeling data as a graph is to traverse a chain of linked nodes, one useful way of thinking about nodes is that they are waypoints along the traversal route. They contain information you need to decide which links are good ones to follow and which ones should be ignored. And relationships are those links. So in this particular slide, Jane and car are nodes, otherwise known as vertexes. So now let's define the relationship. And in this example, you see Jane owns the car. Relationships are links between nodes. In their simplest form, relationships need not contain any information other than which the two nodes they link, but they can and often do contain much more. For example, relationships can include a direction. Jane owns a car is a very different relationship than a car owns Jane, although with self-driving cars, who knows what's going to happen. Relationship directions are required in this particular graph database tool. In addition, relationships can contain any amount of additional metadata, such as a weight or a relationship type. For example, the relationship between Jane and her car is of the type owns. Like direction, type is a required element of the relationships, although other metadata can be optional. The purpose of the data attached to the relationship is to reduce the need to gather and inspect, where you follow all relationships from a given node, then scan the target node data to determine which hops were good and which ones you can discard. This does not scale well. Instead, we use the metadata attached to a relationship to preemptively filter which links to follow during a traversal. So in addition to the basic graph components, one vital concept within graph theory is traversal. As mentioned before, the main point of graphs is to follow a chain of nodes and relationships. The process of finding such routes is the definition of traversal. This is a fairly straightforward concept, but for the sake of clarity and precision, we will take a moment to discuss the different ways a graph can be traversed. Broadly speaking, there are three types: walks, trails, and paths. A walk is the most basic of these. It is simply an ordered alternating list of nodes and relationships. For example, in this simple graph, we could define a walk starting at node 1, then hopping to 2, then 3, back to 2, onward to 6, and back to 2. There are no restrictions here, and you can use relationships multiple times and visit the same node as many times as you wish. This may be your driving pattern if you are driving around town doing some errands. Now let's look at a trail, which is somewhat more restricted. A trail is a walk in which no relationships are repeated. You can still visit a node as many times as you want, but each link can only be used once. For example, remember the 7 bridges problem. The desired traversal in that case is a trail. You can visit each landmass as many times as you like, but can only cross each bridge once. By contrast, the walk we just performed, 1, 2, 3, 2, 6, 2, is not a valid trail because we traversed the relationship between 2 and 3 2 times. Instead, a valid trail could start at 1, then go to 2, 6, and then back to 2, and this would be permitted because there are 2 relationships between 6 and 2, and we use each of them once. And finally, let's talk about a path. This is a trail in which no nodes are repeated. Stated another way, path is a walk in which all items are unique, nodes and relationships both. The trail we just followed, 1, 2, 6, 2, is not a valid path because it visits node 2 twice. Drop that last hop, and this becomes a valid path. So, in summary, a graph is a data model consisting of a set of nodes linked by relationships. And the purpose of modeling data as a graph is to enable traversal. There are multiple traversal types, the most important of which is a path, which is an ordered alternating set of nodes and relationships in which all items are unique.